Hello everyone, my name is Shruti Kesti. I'm working as assistant professor in Department of Computer Science in ABES Engineering College, Ghaziabad. Today I'm going to discuss about the Dijkastra algorithm. We will discuss about the shortest path problem, types of shortest path, what are the shortest path, single source shortest path algorithms, and we will discuss about the Dijkastra algorithm and the complexity analysis of this algorithm. First, we will talk about the shortest path problem. What is shortest path problem? Shortest path problem is the problem of finding a path between two vertices, or you can say two nodes in a graph, such that the sum of weights of its constituent edges is minimized. Yes, in order to find a path between two vertices in such a manner that the sum of weights of each edge lies between the path should be minimum. We can find the shortest path for the directed graph, for undirected graph, and also for the mixed graph. When we are talking about the shortest path, there are two types of shortest path. First is single source shortest path. Second is all pair shortest path. Single source shortest path means single source shortest path algorithm is used to find the shortest path between a particular node to the other nodes. When we are talking about the application of Dijkastra algorithm, or in real world example, you can say that the Google map is also using the shortest path algorithm. When you are giving a source node from where you want to start, and when you are giving the destination node also, then Google map will search all the possible paths and will reflect the shortest path. That is the single source shortest path. And second is all pair shortest path. The all pair shortest path algorithm is used to find the shortest path between each and every node to the other node. Here we are defining the network in terms of graph. In graph, we will contain vertices and edges. So when we are going for the single source shortest path, we will choose a single vertex as a source node. And then in case of all pair shortest path, we will consider all the node as a source node and as well as destination. Single source shortest path. In this, we first initialize a single node source as a source node and find the minimum distance between the source node to all the other nodes to the graph chain. Just take an example in which consider a situation in which a person is in city A and wants to go to city D. There are many paths possible between A to D. Here from this graph, we can see that from A to B, you can move from A to B, from B to C, and then from C to D. This is also a path from A to D. Then how to calculate the cost of in these paths? From A to B, you have the weight edge that is containing the weight of 10. From B to C, you are containing an edge which is having the weight 2. And from C to D, you have an edge which is containing the weight 9. So calculate the complete cost of this path from A to D. You need to add all the weight of these edges. And when you are adding this one, you will get the 20. From this, you can calculate all the path from A to D. Here, there are multiple paths from A to B, A, C, then D. Again, you can go for the from the A to B, then E, and then D. Similarly, you can also choose the path from A to B, B to E, E to C, and C to D. Or A to E, E to B, B to C, or C to D. Similarly, there's also two paths from A to E, E to C, and C to D, and A to E and E to D. From all the path, you can choose the minimum weight path. Here we have calculated the cost of each and every path. Here you can see that the minimum cost is what? This 5. You can say that from A to D, what is the shortest path? That is from A to E, move to E to D. And this will give the cost of 5. So Dijkastra algorithm is also focusing to find out the shortest path between two nodes. Here, there are two algorithms for the single source shortest path. First is Dijkastra algorithm, which we are going to discuss in this video. And second is Bellman-Ford algorithm. Dijkastra algorithm is a single source shortest path algorithm in which we find the shortest path between the source node to other node. It takes a weighted graph as an input and gives the shortest path between the source node to the other nodes. We can apply Dijkastra algorithm only when the graph is directed, that is a limitation of Dijkastra algorithm, weighted, and weights are non-negative. When the particular edge is containing a negative weight, it will be better to do not go for the Dijkastra algorithm. Dijkastra algorithm is applicable in case of directed graph, weighted graph, and weight should be non-negative. That means positive. This is the algorithm of Dijkastra. Here in Dijkastra algorithm, we are passing the complete graph and weight and also passing the source node. Which node will work as source node? Then we will initialize the single source. That means you are initializing all the vertex of a particular graph. How to initialize this one? We'll go for this algorithm. This is the subroutine of the given algorithm. Here you are defining the vertex of each and every vertex of graph. First, for each vertex of graph, you will define a loop and provide the weight of that particular vertex, each vertex as infinity. For each and every vertex of graph will have a weight initially as infinity. And here I'm also initializing a new array which is containing the address of your parent node. You mean to say that if you are choosing the path A to B, it means for B, A is the parent node. Here is defining that from which node you are reaching at the B node. And initialize the value of source node, weight of source node as 0. This is the initialization procedure of your graph. Then initialize and set as empty. This is defining the set value and pass all the vertex to a priority queue. Queues are containing all the vertex and then start a while loop which will work until the queue is empty. Here you are extracting the minimum value in which priority queue you will extract that vertex which will contain the minimum value. In case of initialization, you can see that all the vertex is containing the infinity weight, but only the source node is containing the weight as a 0. In that case, you will get the source node. And after fetching that value, you are passing this value in the source set. You are adding that value in the set, and this will get complete only when all the vertex you have covered. And then for each vertex you are fetching, you need to access all the adjacent nodes of that particular node and then follow the process of relaxation. What is the meaning of relaxation? Relaxation is just saying that when you're passing three variables here, u vertex, v vertex, and w vertex. Here you are considering that vertex v is here, u is here, and v is here, and you have an edge from u to v. U is containing some weight, and v is also containing some weight, and this edge will contain some weight also, right? In that case, if the value of d of v, it means the weight of your vertex v is greater than the sum of weight of your vertex u plus weight of the edge from u to v. In that case, relax that vertex v by updating the value of weight by the sum of weight of u plus weight of u to v h, and also update the parent node. That means v is getting the minimum value by the u, so u will become the parent of v. These all processes following basically greedy algorithm. When you are talking about the Dijkastra algorithm, actually Dijkastra algorithm is following the greedy algorithm. What is the meaning of this greedy algorithm? When you want to create an algorithm, you need to follow one procedure, how to process the steps. As this name suggests, greedy. Greedy means when you are getting any local benefit, then go for it. In Dijkastra algorithm also, when you are getting a minimum weight, you are extracting the minimum value by using the extract min. So you will go for the greedy process. When you are talking about the complexity of greedy Dijkastra algorithm, then In case of 1, when you are storing all the information, AI stores the information about edge I comma j. And when you are searching all the distance, you need to access all the vertex. V is the number of vertex in your graph. And when you want to access all the neighbors of this, how many vertices, or you can say how many edges should be there when you have a complete graph. When a graph is complete, each and every vertex will have maximum v minus 1 edges. It means every node is connected with the each and every node. In that case, you need to access that thing by v minus 1 times. So when you are calculating this value for each one, you need to multiply this value v minus 1, or you can say the complexity will be O of v square. V is nothing, it's a number of vertices in your given graph. And this is the complexity of Dijkastra algorithm in case first case. In second case, when you are using the breadth first search to traverse all the vertices in your graph, in that case, you will need to use the complexity of O of v plus e. This is the traversing way. BFS, that is breadth first search, is a way to traverse particular node in your graph. And for extracting the minimum value, you are using the min heap property. When you are taking the min heap property, you will have a complexity of O of log v. Then when we multiply this value, you will get the value of O of E log v. This is the average case complexity of your Dijkastra algorithm. When we are talking about the drawbacks of Dijkastra algorithm, then here you can see that Dijkastra algorithm is not applicable when the weight is negative. How you can you say that this is not applicable or you're not getting the optimal solution? Here we can take the example. Suppose 1 is the source node. Just you need to initialize the variables. All the vertex, initialize source node as a 0 and other vertex weight is containing the infinity. Now, access the node S, that is starting node, and access all the adjacent vertex of your 1, that is 2 and 4. Now 2 is what? Your v, and the weight of this v is currently this is infinity. And what is u? That is 1. Weight of this one is 0, and the weight of u comma v, or you can say weight of h from 1 to 2 is 3. So here you can see that the infinity is greater than 0 plus 3. You can relax this value by updating the value infinity into 3. Similarly, the weight of the vertex 4 will get also relaxed. Why? Because the weight is infinity, and when you are talking about the 0 plus 5, that is 5. 5 is less than the infinity. So you can again update the value of vertex 4 as 5. Now again use the greedy algorithm. You have weighted 3, 5 and infinity. Because 1 is already visited, you cannot go back to the vertex 1. Here 3 is the minimum value, fetch this value. But from 2, you are not drawing any edge to other vertex. So in that case, after visiting 2, you will not update any weight. Now next value, what is the minimum value? 5 and infinity. 5 is the minimum value, choose this one. When you are choosing this value, so what will be the value of 3? This will get updated because what? Why? Because d of u is what? This time 5. D of u is 5. This is on 3, this is on 5, and this is on infinity. Infinity is greater than 5 plus weight of 4 to 3 is 2, that is 7. So you can relax this vertex as 7. Now 4 is also visited, 1 is also visited, 2 is also visited. Now, when you are visiting the node 3, from 3 to 2, you have an edge which is containing the weight minus 5. If you are using this value, then 7 minus 5 will give you 2. But this time 2 is containing the weight 3. But in Dijkastra algorithm, if you have visited a particular vertex, you cannot go back to that vertex. So you cannot update the value of 3. Even though by using your graph, your 2 vertex should have minimum value 2, but you are containing 3 value. Then this is not giving you the optimal solution because you are choosing the local values. That's why this Dijkastra algorithm is not applicable in case of negative weight. It gets failed because it's not giving the optimal solution. These are the references, and thank you so much.